This image shows us the process of creating a sampling distribution for a proportion rather than a mean, and a lot of the idea is the same as that for a mean, but we have an illustration here where we want to imagine that this is based on an urn full of blue and red balls. Statistics and probability use lots and lots of urns full of colored balls. So in this case we have blue, a whole bunch of them. We have red. Looks a little bit too deterministic here. Try and increase the randomness a little bit. And there are 100 of each, as we can see from this frequency distribution right here, this bar chart. We have 100 of each, and in each of these samples, if we look at this first sample here, we can see that the proportion that's being calculated is 8/20. And looking at the chart, we can see then that 8 is really the number of red balls. So the proportion being calculated is the proportion of balls in each sample that are red. So that is the proportion that we are tracking. We see that that's the same for all of these. Now in this sampling distribution, which looks more like a histogram than a dot plot, the same idea still applies. Each of these bars can be considered a stack of dots, and each dot in this is a sample proportion. Now see that this distribution over here on the left describes our population. The population is that we have 100 of each ball, and that our population parameter is p equals 0.5. This is a distribution over here on the right for the sample proportion p hat, and we can see that this distribution is centered at the population proportion of 0.5. So just like with our means, we saw that our distribution, our sampling distribution, did seem to be centered at the population mean. Here we see that our sampling distribution is centered at our population proportion, whatever parameter it is that we could estimate with these statistics that we're collecting up. So this is a sampling distribution for one proportion, and one thing that we're going to do that we didn't do with our means but we could have is to estimate the standard error. Remember that standard error is the same thing as standard deviation once you're looking at the distribution. So the methods that we learned for estimating standard deviation work for estimating standard error in a sampling distribution. And in particular, this looks approximately bell-shaped. So we're going to use the 95% rule to do this. I would say the center 95% of this distribution looks like it sits between about 0.3 and maybe 0.7 or 0.75, right? Anywhere in here is a reasonable place to start this estimate. So the center 95% goes from 0.3 to 0.75. I want to take that whole interval and divide it by 4, because remember that the center 95% goes from 2 standard deviations below the mean to 2 standard deviations above the mean for a total span of 4 standard deviations. So I would suggest referring back to the section in which we first introduced standard deviation and the 95% rule if you don't remember how to do this. But what we're going to do is take the upper bound of that central 95%, so my 0.75 is the upper bound, subtract off the lower bound, and divide this whole interval by 4 because we span 4 standard deviations. So bringing in a calculator for this gets me 0.75 minus 0.3. And then when I divide that by 4, I get 0.1125. I could round that off to 0.11 if I want to, right? So this is approximately 0.11. We're not looking for extreme accuracy in these, so this here is fine. If I had chosen 0.7 instead of 0.75, I would have come up with just 0.1, which is also a perfectly reasonable estimate. It's more about demonstrating the process and choosing somewhat reasonable bounds for your center 95%. In general, when we're using software and we're given a data set, we let StatKey calculate these things for us. If we're just given a graph and asked to estimate the standard error from the graph, that's when we would use this 95% rule. So we're going now to go on to a StatKey tutorial, and this one is going to involve the Hollywood Movies dataset, which is also considered a population. First, let's go to descriptive statistics for one categorical variable, because we want to find the proportion that we are working with. We need our population proportion in order to get this whole process started. The sampling distributions page for a proportion doesn't really allow you to just bring in a data set. You have to go there already knowing the proportion. So we're going to find the proportion of movies whose genre is comedy, and then write that down using correct notation. Since that is a population proportion, I'm going to call it P. So here we are in StatKey. I'm going to descriptive statistics and graphs for one categorical variable. I will upload the file Hollywood Movies. And choose the variable genre. And look over here for comedy. The proportion I get from that is 0.256. So we'll go ahead and write that down. P is equal to 0.256. This is the population proportion based on which we are going to create a sampling distribution. So now we'll go back to the StatKey main page and go to Sampling Distributions Proportion, and we'll click on Edit Proportion to enter this value. So back to the StatKey home page. Sampling distribution for a proportion is here. Edit proportion, I'm going to enter 0.256. All right, so we've done this. Next, we're going to choose samples of size n equals 10, which is the default anyway, and generate one sample. And we will write the value of the sample proportion using correct notation. We already know that's a sample proportion, so the p hat part we can write now, but we'll come back to StatKey to get the value. So, oh, I'm sorry, 10 is not the default for proportion, it's 200. So I'm decreasing that to 10, and then generate one sample, and it looks like this sample is, the sample proportion is 0.4 for me. It of course will come out differently for you if you are following along and doing these steps on your own. Now we can generate 1,000 samples. You can either reset the plot or not. I like having a nice round number, so I'll go ahead and reset first. And we can see what this graph looks like. It looks approximately bell-shaped, but a little bit of right skew, just due to the fact that the left side gets cut off a little bit. We can also see our mean and standard error up here. Our mean is 0.268. Our standard error is 0.139. The 0.268 isn't too surprising because we know that this should come out centered pretty close to our population proportion. And if we generate more samples, we expect it to stabilize and get a bit closer. Okay, so we have a mean of 0.268, a standard error of 0.139, fairly close to bell-shaped other than the fact that the left tail is cut off, which leaves us with some right skew. We're going to change our sample size to n equals 10, and generate 1,000 samples to get a new graph, and we can reflect back on what we saw with the sampling distribution for a mean and guess what's going to happen. 1,000 samples, that doesn't have any real effect other than stabilizing, but the n equals 100, increasing our sample size from 10 to 100, should make that standard error, this value right here, get smaller. So we're expecting to see that get smaller. So coming back here, I'll reset the plot, choose samples of size 100, and generate 1,000 samples. I see that my mean is still pretty close to the population proportion. We're at 0.257 now, and my standard error did get quite a bit smaller at 0.045. I also see that the distribution looks much closer to bell-shaped this time. Because the standard error got smaller and the graph got more concentrated at the center, we're no longer cutting off that left tail like the problem that we had with n equals 10. So we lost that skew and we've gotten something much closer to bell shape. So the mean may be stabilized a little bit more with a larger sample, but there's no real trend in what you're going to see with the mean as n increases. The standard error definitely got smaller. The graph got more concentrated at the center. You don't really notice that because the scale changes, but it is more concentrated at the center, which we know by the fact that the standard error is smaller.